Okay, today I'm going to hopefully show you a much faster way to graph a lot of these rational functions that we've been working with. To really graph them quickly though, you have to know the parent function. And that one looks like what we have right here, f of x equals 1 over x. So let's use what we've learned so far of how would we graph just this parent function. You guys know that the first thing we'd start with is what would be the vertical asymptotes or holes. And to determine that, you set the denominator equal to 0 and solve. So in this case, there's nothing to solve for. I just get x equals 0. What is that? Is that a vertical asymptote or is it a hole? Vertical asymptote or a hole. Awesome. How do we know it's a vertical asymptote? Good, it doesn't cancel. So I know from this graph, I could go ahead and graph that VA, which has a dashed line all the way through at x equals 0. Okay, it has no holes. So the next thing I'd be looking for is what is the horizontal asymptote? Remember, the horizontal asymptote, you look at the degree of the numerator and the degree of the denominator. What's the degree of the numerator? Awesome, x to the 0. So 0, I could say, what's the degree of the denominator? 1. So since 0 is less than 1, what type of horizontal asymptote will it have? Good, y equals 0. So I would go ahead and I'd plot that horizontal line at y equals 0. And then we know we could find the x-intercept and the y-intercept. But just to save time, if I'm looking at the fact that there's a vertical asymptote at x equals 0, will there be a y-intercept? Will there be a place where it crosses the y-axis?
No.
No. How about an x-intercept? Will the graph cross the x-axis? No. So I know there's going to be none. But if you're looking at, well, wait, we did a bunch of algebra to figure that out. To find the x-intercept, you would set y equal to 0 and solve. So if I took this equation, which was y equals 1 over x, and I set y equal to 0, do I need to put the x in the bottom? No, if you did, you would just multiply it out when you were solving. And x times 0 gives me 0. And then can 0 equal 1? No. So that's how I know x-intercept, there's none if I didn't see it visually on the graph. And same with the y-intercept. If I was looking at the y-intercept, I would set x equal to 0. So if I do y equals 1 divided by 0, can you have 1 over 0? No, that's undefined. So there's no y-intercept, which can be confirmed algebraically using algebra or visually on the graph because there's asymptotes there. Okay, so the next thing we would look at is how do I determine what the shape of the graph looks like? If I don't know what's happening to the right or the left of the vertical asymptote, what can I use? How did you guys find points if you had a table? Good, we'll use a table. So if I use a table, I have y is equal to 1 over x. And I want to plug in numbers to the left and to the right of the vertical asymptote. So what would be a number to the left of 0? -2 would work. I could plug in, you know what, for right now, I'm just going to plug in -1, but I could have chosen -2, which would have been totally good. But if I plug in -1, this point is pretty easy to remember. If I plug in -1, what am I going to get out for y? -1. So this point, -1, -1, that's pretty easy to remember. And that will always happen on this parent graph, y equals 1 over x. And then you guys know, based off of the work we've done with rational functions, the graph is going to get close to the asymptote, but never touch it. Same over here. And then if I plug in 1, I'll get 1 over 1, which gives me 1. So I have the point 1, 1. That's another pretty easy point to remember, and that always exists on the parent graph. So I have I have the graph going up towards x equals 0 and to the side towards that horizontal asymptote. So here's the pieces to remember. This is another parent function. If you guys remember from the bell ringer, once you know the parent function, when numbers are added or subtracted, you can just use your rules of transformations. I know this is new, so you do want to remember that y equals 1 over x is a parent graph. and it has points. The easiest ones to remember are probably 1, 1 and -1, -1. And it always has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. We're going to be graphing the parent graph like 6 times. So hopefully by the 6th time, you'll remember that information and be able to use it to graph quickly. All right, after we've discovered what the parent function looks like, we can use any numbers that are being added or subtracted to the x in the parent function to help us move the graph left or right. We can use any numbers added or subtracted outside of the x to move the graph up or down. And we can reflect the graph over the y or the x axis using those negatives in front. We're not going to be doing vertical stretches or shrinks with these parent functions. So let's go ahead and see, well, what does this look like if we move it left or right? Recall with something you've already done, which is a quadratic. How does this graph, f of x equals quantity x plus 5 squared, differ from the basic parent graph? How would this graph move? Well, if I'm thinking about a quadratic, right, it's going to have this. But you're right, you're on the next one, which I'll come to because you're ahead of the game, Allison. How does this graph move from this one? Good, left 5. And the key that you have to be able to recognize is that the plus 5 is with the x. So in this new graph, when the plus 5 shows up inside with the x, in fact, I could put parentheses around it if I wanted to, because there's always invisible parentheses recognized in the denominator. When it's inside with the x, it's going to move left or right. In this case, how do you think this graph is going to move? Left, good. It's going to go left 5 units. So we're going to use our parent graph. I'm going to call it P of x just to say it's the parent graph. The parent graph from this one would be 1 over x. And I'm going to use the data that I found above. So I'm going to use points like 1, 0, or sorry, not 1, 0, 1, 1, and -1, -1. And then the vertical asymptote and the horizontal asymptote. And then I'm going to move this graph to graph function f. So the parent graph would have a VA like this. It would have an HA like this. It has those points here and here. And the shape of the graph shows up in this manner and this manner. Now I'm going to take this graph to graph function f. And rather than doing all the tables and all the fancy work, I'm just going to move this graph left 5. Probably the best thing to do is start with the asymptotes. If you move this graph left 5, where will the vertical asymptote be moved to? -5. It'll go 1, 2, 3, 4, -5. So now I know that the vertical asymptote, and this might be helpful to write down, the vertical asymptote moves to -5. Think about the horizontal asymptote. If the horizontal asymptote, which goes forever left and right, if that shifts to the left 5, is it going to change its current location? Nope, it's going to still go forever left and right. So the horizontal asymptote doesn't change. But now I'm going to take this entire graph and shift it left 5. Just use that 1 point, 1, 1. Move it left 5. Go 1, 2, 3, 4, 5. It shows up in the corner there. And then take this point, which is down here, and move that left 5. 1, 2, 3, 4, 5. It shows up in the corner. And then we know all of those points move left 5, so I can go ahead and create the sketch. It's going to go like that, and it's going to go like that. Once you've graphed your new graph, you do not need the parent anymore. You can erase it because it's not actually your answer. You're graphing function f, which is the pink one in my case. Any questions on that? All right, on to the next one. Turn to your partner and tell them, how will this graph move from the parent graph? All right, I heard it, right 5, okay. So let's go ahead and let's use that parent graph again. P of x equals 1 over x. Let's see if you remember it by now. It has a vertical asymptote at x equals 0. It has a horizontal asymptote at y equals 0. It has points of 1, 1 and -1, -1. And then it continues in this shape, going up like this, and then this way, and then this way. But now to graph function f, I'm going to take everything and move it right 5. I always suggest start with the asymptotes. So where will the vertical asymptote move to? If I take x equals 0 and I go 1, 2, 3, 4, 5, where does it move to? Well, that point is going to move, but where will the entire vertical line move? 5. 1, 2, 3, 4, 5. So it's going to move to x equals 5. So the vertical asymptote moves to x equals 5. Is the horizontal asymptote going to change its current location? No, it's going to continue going left and right forever. But now I'm going to take those 2 points, which I said, hey, try to memorize these, hold on to them, and move them right 5 units. So I'm going to go right 1, 2, 3, 4, 5. I'm going to move this point right 1, 2, 3, 4, 5. And then I know that this shape is going to go towards the asymptotes, not touch them. It's going to go towards the asymptotes, not touch them. And I can go ahead and erase the original parent function because it just helped me sketched. It's not actually part of my answer. Any questions on that? Okay, we've got 3 more shifts, and then that's how you can graph these functions pretty quickly. The next type of shift is, how do you know if the graph's going to move up or down? Look back at something you already knew. You already know about quadratics. If the +5 is added outside of the input or outside of the x, how did it move in the previous chapter? Up 5. So what does that look like with our new function? The number is going to be added or subtracted outside of the x, like this case right here. So how do you think this graph is going to move from the parent graph? It's a -3. Down 3, awesome. Let's graph that parent graph again. P of x is 1 over x. So I'm going to go ahead and sketch x equals 0, y equals 0, the points 1, 1, and -1, -1. And I know the graph looks like this. Now I keep telling you guys start with the asymptotes. Which asymptote is going to move here? Is it going to be the vertical asymptote or is it going to be the horizontal asymptote? Horizontal asymptote, because the graph is moving down 3. So where will the horizontal asymptote move to? Down 3 to -3. 1, 2, 3, -3. So then the horizontal asymptote is at -3. Yeah, Allison.
How is that it's like outside of the equation?
Good question. So what you would look at is we've never had a number added or subtracted outside yet. And what you would be looking at is if I look at the horizontal asymptote of this is an x to the 0 over an x to the first. So that's at y equals 0. But all of these points, if I'm looking at what the y values are approaching, they're approaching 0, but then I'm subtracting 3 from each of those values. So if I'm looking at like 0.000001 minus 3, then it's going to show up at like 2.999. So it's going to approach -3. So you can still use your understanding of horizontal asymptotes within the fraction, but you do need to recognize that the -3 is going to shift the entire graph down. Good question. And Allison, you're actually bringing up a really good point. All of these transformations only work if you have a 1 over x or a 1 over that form. If I asked you to graph like x squared minus 4 over x minus 2, does this have the parent function 1 over x? No. So I'd have to go back to how do we graph a rational function? So today's lesson is just kind of like, if you remember your transformations, there's certain graphs you could graph way quicker than going through all the steps. Good question. Okay, so the horizontal asymptote moves to -3. What's going to happen to the vertical asymptote if it shifts down? Is it going to move at all? Nope, it's just gonna slide down, which means it's gonna still continue to go forever up and down. And then I need to take each of those points and move them down 3. So I'm going to take 1, 1, move it down 3 points, and now it'll go down to 2, 1. There you are. The heck. Okay, so I'll take that point, go down 1, 2, 3. So now it goes here. I would take this point and move that down 3, 1, 2, 3. Now it goes here. And actually, once you have those points moved, you can really erase the original graph. Because when you have a point on the graph always goes through that point, gets close to the asymptote, but doesn't touch. And it goes through this point, gets close to the asymptote, doesn't touch. All right, on to the next one. The next one, I'm going to have you work through this one with your partner, but I'm going to ask the person who would live the farthest away from here if you can share how this graph's going to move from the parent graph.
Oh, well, I take it. Oh, no, not this. Oh, no, no, we just. Oh, this is reflecting on that. Oh. This one. In the same place. Yeah. Okay, I like it. It's just. I love throwing. I like to draw. It should be. Well, like, look at how satisfying it is. The same. I like taking notes. I like taking notes. No, yeah. I don't know because I don't have room. So the easiest is to start with the accent. Because if I don't, I don't have to go back and be able to understand So they were a charge last night because the magnet didn't plug in. Like your doesn't
I think you can do it here. All right, guys. Some of you recognize that if you just start with the horizontal asymptote, this one's going to go up 3, so I'm going to have a horizontal asymptote at y equals 3. There's no change to the vertical asymptote because there's nothing added or subtracted to x. And then once you memorize kind of the location of those 2 major points, you really don't even need the parent graph. You can just kind of quickly sketch what this one should look like. All right, 2 other types of transformations we're going to look at. Recall with one you've already done, like the x squared. If there's a negative in front of the x squared, that's going to take the original parent graph and it's going to reflect it over, I always think upside down, but it's really going to reflect over the x-axis. So this one's the x. Yeah. Yeah. Because there's nothing added or subtracted to x in the denominator. That's when it switches left and right. Right. Yeah. Good question. All right, guys. So in this new function, when the negative is outside, so when it's not with the x in parentheses, it's going to reflect over the x-axis. So let's start with our parent graph. And this one you will want to sketch the parent graph just so that you can visually see the change. So my parent graph is 1 over x. It has points like 1, 1, -1, -1. It has a vertical asymptote at x equals 0. It has a horizontal asymptote at y equals 0. And we know that it's sketched up like this. If you reflect it over the x-axis, you're going to take really this part of the green shape, the one that's on the top, and you're going to reflect it upside down. So the 0.11 is going down to 1, -1, and all the other points which were approaching 0 are still approaching 0, but below the x-axis. And all of these points which are approaching positive infinity are now going to be approaching negative infinity. Really, they're reflected over the x-axis. And then same with the other way. If I reflect this point up, then it's going to go ahead and reflect up here as well. Now I can erase the parent graph because it's not part of my answer, but I do want to visually see that shift. All right, you're about to see that if you reflect it over the x-axis or the y-axis, it's actually the same thing for this graph. So at least you don't have to worry about, hey, how does the reflection work? Even if you say the wrong axis, it's actually will end up being the same equation. But for review purposes, hopefully you remember that when the negative is inside with the x, that's going to reflect over the y-axis. Reflect over the y. So how does that visually look in this new equation? Well, the negative shows up inside with the x. That's technically a reflection over the y-axis. Let's see what happens when we take that original graph and we reflect it over the y. So again, my parent graph looks like this, 1 over x. So if I graph those points again of 1, 1, -1, -1, and I know it goes up towards 0, to the side towards 0. Now, if I think about reflecting this over the y-axis, the part that's to the right of the y-axis gets reflected to the left of the y-axis. So it goes like this. And the part that's to the left of the y-axis gets reflected to the right of the y-axis. But if I erase the original shape, what do you notice about this graph in comparison to the last graph that we did? It's the same thing. So really the reason being is because you could multiply this by -1 over -1. And then you can see f of x is actually equal to -1 over x. So it's actually the exact same equation. The beauty of that is all you have to remember for reflections is that it's in opposite corners. The graph shows up in opposite corners. Okay, let's put these pieces together and see if we can try the 3 sample problems from below. Letter A, the first thing I would ask is, how is this graph going to move? The -2, how is that going to shift the original graph? Right to, awesome. And remember I said start with your asymptotes. Where is that going to move the vertical asymptote to? Good, 2. The +3, how is that going to move the graph? Up 3. So where will the horizontal asymptote move to? 3. This is my preference. If I know the graph's going to move right 2 and up 3, you can start with the parent graph, but I prefer to start with the asymptote. So the vertical asymptote is going to shift to the right 2. So now it's going to be at x equals 2. The horizontal asymptote is going to shift up 3. So it's going to shift the entire graph 1, 2, 3. And now the new horizontal asymptote is going to go here. And then those 2 points, I know that I'm shifting them right 2 and up 3. So they're going to end up in this corner and this corner. And now I don't need that original parent shape. I can go ahead and sketch the fact that the graph will look like this in this corner and this in this corner. All right, letter B, go ahead and try letter B on your own. If you are unsure, raise your hand, I'll jump straight to you.
Yeah.
All right, guys, I'm seeing really good things. X plus 1 is going to move the graph to the left one. So the VA is going to move to -1. -2 is going to go down 2. So the HA is going to go to -2. And then you have those two kitty corner points. It's going to move the graph, or the graph will be shaped like this, and it will be shaped like this. Some people even went on to letter C. Letter C, though, we do have to make note. What is the negative going to do to the original parent graph? Is it still going to be in this corner and this corner? No, it's going to reflect it. And here's the beauty of this function. It actually doesn't matter if you say over the x-axis or the y-axis. You're both correct. So I'm just going to say it's going to reflect. And then what will the +2 do to the graph? Move it up 2. So I'm going to take that HA. I'm going to move it up 2 like that. What's my VA going to be at? 0, it's not going to move. But now the graph, which originally was here and here, gets reflected. So the new point is here and here. And the entire shape looks like that, and that, and that, and that-ish. All right, I told you guys we were going to take a break after this lesson, go over the tests, and then we'll finish up. I know it's a lot today, but you can rest with the fact that most likely we'll get through this and there'll be no homework tonight. Okay, Kylie. Yes, Margot, you can go too. All right, let's go ahead, grab that test, take out a different colored pen. Alyssa, can you step out? Jalen, can you step out?